So a few words of caution as we move about this chapter. So here's some cautions on confidence intervals. A sampling distribution shows how a statistic varies in repeated random sampling. The variation causes random sampling error because any statistic misses the proof parameter by a random amount. Remember, if we're taking a sampling distribution, it still fits a normal distribution. More data is going to align closely to the mean, but all is going to be a little off, right? The margin of error in a confidence interval ignores everything except the sample-to-sample variation due to choosing the sample randomly. But the margin of error doesn't cover all errors. It only covers random sampling errors. And there are some practical difficulties, such as underconfident coverage and non-response, that are often more serious than random sampling error. And the margin of error, it doesn't take such difficulties into account. So I just wanted you guys to be aware. So here's some cautions about significant tests. Significant tests are widely used in most areas of statistical work. Some points to keep in mind when we use or interpret significance tests are to follow. So first, how small a p is convincing. I've been telling you less than or equal to 0.05, right? That means the odds of it occurring are less than or equal to 1 in 20, right? The purpose of a test of significance is to describe how convincing the evidence provided by the sample against the null hypothesis is. So how small a p-value is convincing evidence against the null hypothesis depends mainly on two circumstances. So first off, if our null hypothesis represents an assumption that has been believed for years, that's strong evidence, a small p will be needed. If rejecting H0 means making costly changes, you will also need strong evidence, okay? Continuing our cautions about significance tests, significance really depends on the alternate hypothesis. The p-value for a one-sided test is half of the p-value for the two-sided test of the same null hypothesis based on the same data. The evidence against the null hypothesis is stronger when the alternate is one-sided because it's based on the data plus information about the direction and deviations from the null, right? We don't have to multiply our data times 2, right? It's half the size. And if we lack this added information, like if we aren't sure which direction it's going, we just want to assume it's different, right? 2A is not equal to, one-sided is less than or greater than. We can always use a two-sided hypothesis. Last cautions about significant tests, right? Sample size affects our statistical language. Because large random samples have little chance variation, very small population effects can be highly significant if our sample is large. Because small random samples have a lot of chance variation, even large population effects can fail to be significant if our sample is small, right? We need to be taking a large random sample. Statistical significance does not tell us whether an effect is large enough to be important. That is, statistical significance is always not the same as practical significance, kind of a key takeaway. Last but not least, beware of multiple analyses. Assessing statistical significance works well if you decide what effect you are seeking. You need to design a study to search specifically for that and use a test that will weigh in on the evidence you get. So in our next video, we're going to talk about planning a study and then walking through a couple of discussions of errors.